Okay, so now we're looking for the forced part of the solution. We found the natural part. And so we have to go back to the original differential equation. And notice what I did. I took what we had there, which was something like d vs dt plus 6vs, and I just went ahead and I substituted in, for part A, what our source voltage is. And it is a function of time. Look, it's a decreasing exponential. In part B, it's a constant, so that's going to be a little bit easier, but let's do part A, which is the harder part. So I just went ahead and, the derivative of 6e to the minus 3t, and then plus, anyway, whatever it was. So here now is our forcing function, 18e to the minus 3t. So I need to look for the forced part of the solution. Here's how you do it. You guess a solution of the same form as the forcing function. So I'm just going to take a wild guess, not a wild guess. I'm going to guess that my solution is, and I don't, call it some constant m. I don't know what the constant's going to be, but I want the solution to have the same form as the forcing function. So it's going to be some constant e to the minus 3t. So I'm going to guess this as a solution. And who knows? It might work. Let's try it. So let's substitute it in, right? If you substitute it in and it solves the problem, then we guessed right. So let's go ahead, and so we're going to have to get the first and second derivative, right? So the first derivative is minus 3m e to the minus 3t, and the second derivative is it's going to be plus 9m e to the minus 3t. So let's substitute those in, okay? So the second derivative is 9m e to the minus 3t plus 7 times the first derivative. So 7 times minus 3 is minus 21 m e to the minus 3t plus 10 m e to the minus 3t is equal to 18 e to the minus 3t. All of the e to the minus 3t terms can cancel out. Solve this equation for m, and you get minus 9. So if m is equal to minus 9, we've got it. We've got a solution. So my guess was pretty good. And that's in general the case. And I have a chart in the notes where basically if you have this form of the forcing function, go ahead and make this guess. But the whole idea is that you're just going to guess a form that looks like the forcing function, but more general. Okay, so we don't know what that constant is going to be. So great, I just found that VF is equal to minus 9 e to the minus 3t. So I have the forced part of the solution, I have the natural part, I'm almost done. So the complete solution, right, because it's the forced plus the natural, looks like this. And the only thing left that I have to do is find A1 and A2. This is the answer. This, on a test, gives you, 90 out of 100 points. Because the only thing left you have to do is evaluate those arbitrary constants. That's it. And again, how do you evaluate the arbitrary constants? You've got to go back to the original circuit and find the initial conditions. So let's do that right now. Can I erase all this? I think so. Okay, but here's what we've got so far. Let me put this up here. So, we've pretty much got the answer. Minus 9 e to the minus 3t. There's the forced part of the solution, and then the natural part of the solution. has these arbitrary constants in it, and that's the only thing left we have to do is figure out what those arbitrary constants are. And we know that to get those arbitrary constants, you have to have the initial conditions. So I need to go back to the original circuit where the switch is in this position at t less than 0. And I need to find I and V. You know, I think because of time constraints, I'm going to let you do that on your own. And hopefully it won't be too hard for you to figure out that the current in this circuit at t equals 0 minus is 1 amp, which of course then, because the current cannot change instantaneously across an inductor, that's going to be the current after t equals 0. So there's one initial condition. And then the other one is the voltage across the capacitor, which cannot change instantaneously. So looking at this circuit at t equals 0 minus, you know, again, I'm skipping the details just because of the time constraints, because I got to get going. But there, it's 6 volts, and so now we know the voltage at t equals 0 plus. So here are the boundary conditions, the initial conditions that we're going to use to calculate those constants A and B. So the first one is relatively straightforward. All we have to do, look, we've got an equation of voltage as a function of time. I mean, that's our solution to the, you know, to this circuit. We found voltage as a function of time. We know that at t equals 0, the voltage is 6. So just substitute those values in. At t equals 0, v equals 6. T equals 0, e to the 0 is 1. So we end up with minus 9 plus a1 plus a2. So basically, I don't know, just putting the, we have a1 plus a2 is equal to 15. Okay, so here's one equation that will help us get a1 and a2. Of course, we need another one, right? Because we need 2 equations to find 2 unknowns. But we found one of the equations. How are we going to get the other one? It's always tricky. Getting the second one is always tricky. At one point, we did Kirchhoff's current law at that node A. Okay, and if you go back to that equation, let me find it. It looked something like this. Where'd it go? Well, it's rearranged a little bit, but it basically looked like, you could get it to look like this. dv dt plus v plus 4I is equal to vs. Okay, so you have to go back to one of those equations that you used to get the second order differential equation. So it's one of those first order differential equations in the state variables. So this was the one that we got from just doing a Kirchhoff's current law at node A. So let me solve this for dv dt and just put everything else on the other side. So we've got vs minus v minus 4I. Okay, the reason I'm doing this is because I can go up to, if I want to evaluate this at t equals 0, I can do that, right? Because I know what v is at t equals 0, and I know what I is at t equals 0. In fact, let's just go ahead and do it. At t equals 0, this is going to be vs minus, what do we find, 6 minus 4 times 1. So it's going to be vs minus 10. And vs, remember what vs is 6e to the minus 3t. So at t equals 0, that's just 6. So 6 minus 10 is minus 4. All right? So I know that dv dt at t equals 0 is minus 4. Is there another way that I can get this? Yeah, look. Go back to this equation, take the derivative, and evaluate it at t equals 0. And then you've got another equation in A1 and A2. I know it seems glitchy. I know this is always the hardest part of these problems. But I'm going to actually end here and just repeat what you're supposed to do to finish it off. We now have dv dt evaluated at t equals 0. It's equal to minus 4. Go back, take the derivative of this equation, dv dt, evaluate it at t equals 0, and set that equal to minus 4. That gives you another equation in A1 and A2. Boom, you've got your arbitrary constants. Now that you've got your arbitrary constants, you've got the answer to the problem. And you're done.